Hello everyone, I'm Moitreya Chatterjee, a PhD student at UIUC, and today I'm happy to present our work titled A Variational Neural Uncertainty Model for Stochastic Video Prediction. This is a joint work with Professor Narendra Ahuja and Anoop Cherian. The task of video frame prediction is to predict a set of frames of a video given a set of scene frames. Mathematically, this may be represented as follows. Given a set of scene frames x1 through xc, the task is to predict a set of target frames x hat c plus 1 through x hat t. Stochastic frame prediction approaches attempt to solve this prediction task by learning a prior distribution on the latent space of the future frames pzi. These models typically sample a stochasticity vector zi from these prior latent space distributions and couple them with the set of previous frames x1 through xc and predict the future frames x hat c plus 1 through x hat t. In this work, we present Neural Uncertainty Quantifier, NUQ, an estimate of the predictive uncertainty of a stochastic frame prediction model using a hierarchical deep Bayesian network. NUQ is trained using a novel hierarchical variational setup that allows for incorporating problem-specific prior knowledge. Our model shows better video generation results and faster training capabilities even with small training sets compared with recent state-of-the-art stochastic frame prediction methods across different datasets. Deterministic frame prediction approaches attempt to learn a direct mapping from the set of scene frames x1 through xc to a set of predicted frames x hat c plus 1 through x hat t. This typically involves learning a recurrent neural model such as an LSTM denoted by f theta. In particular, as shown in the figure here, an LSTM first proceeds to encode the set of scene frames and then attempts to decode these set of scene frames to generate the target frames in a recurrent fashion by feeding back the previous generated frames. Stochastic frame prediction approaches operate in a similar fashion, except additionally, they introduce a stochasticity vector zi sampled from the prior distribution of the latent space of future frames. These are indicated by the red boxes. The likelihood model of the stochastic frame prediction task may be represented by the following system of equations. First, there is a prediction model which captures the distribution learned on the space of output frames xt given the set of previous frames x1 through xt minus 1 and the stochasticity vector zt. Next, there is also the prior distribution on the latent space of the future frames pzt from which the stochasticity vector zt is sampled. We call this distribution the prior. However, estimating the evidence exactly for this setup is intractable since this integral is not solvable exactly for practical purposes. Kingma and Welling attempt to solve this issue by instead learning a variational lower bound on this evidence. This is represented by the equation L theta phi here. The equation consists of two parts. The first one is an expectation term, which essentially reduces to the L2 loss when the distribution is a simple Gaussian with a constant covariance. There is also the KL divergence term, which tries to minimize the difference between the posterior and the prior distribution on the latent space of the future frames. SVG, a popular stochastic frame prediction approach, attempts to learn this prior distribution PZT on the latent space of future frames using a model P-Chi that operates on the frames x1 through xt minus 1. Post-training, P-Chi ideally should mimic Q5, and therefore one could substitute P-Chi for Q5. However, there is a critical problem with the standard stochastic frame prediction setup. In particular, if at any time step a plausible frame is predicted which does not match the ground truth, then the model is penalized heavily via the L2 loss. Let's consider the scenario as shown in the figure here. An MNIST digit is moving inside the box and is colliding with its edges. The trajectory of the motion of the digit is rectilinear, except when it collides at which point it switches to a random direction of motion. As shown here, the digit was originally moving in a horizontal trajectory, starts to move in a downward trajectory. Now, if our model were to predict this trajectory as accurately as shown by possibility 1 here, then our model will not be penalized too much. However, since the direction of motion post the collision is stochastic in this setup, one could also envisage a scenario where the model predicts a slightly different trajectory as shown by possibility 2. However, since this trajectory is different from that of the ground truth, therefore this outcome will be heavily penalized since this realization of frames differs from the ground truth frames. In this work, we attempt to solve this issue by learning the predictive uncertainty of the model associated with a future frame. In this diagram, we show a representation of a typical stochastic video generation network. Note that such models incorporate a stochasticity vector zt in order to predict the future frame x hat t. The vector zt is sampled from a posterior network which looks at frames x1 through xt. Additionally, there is a prior distribution network which looks at frames x1 through xt minus 1 that is chained to the posterior network via the KL divergence. Post the training, potentially the prior and the posterior distributions should match, and one could potentially get rid of the posterior distribution altogether and could sample zt directly from the prior distribution at this time. In our formulation, we seek to augment this typical stochastic video generation setup with a variance encoder-decoder module, which is tasked with predicting the uncertainty of the future frame Bt, given the covariance of sigma Tz as input. As before, we will get rid of the posterior network at test time. Rather than assuming a distribution with a constant variance for the data likelihood, NUQ derives it from the covariance of the stochastic prior. This yields our uncertainty measure 1 over Bt and is represented by the equation below. We derive the uncertainty measure from using a conditional variational autoencoder which takes sigma Tz as input. The network consists of an encoder network Q lambda which takes as input sigma Tz and a decoder network P nu which is responsible for predicting the uncertainty Bt. With this setup, the updated likelihood model of our formulation is shown in the equation here. Here we show a more detailed representation of our model's architecture, including the variance encoder network, the variance decoder network, and the input to this module, which is the covariance matrix of the prior network, and the output, which is the uncertainty on the predicted frame. Note that this encoder-decoder leverages a user-defined hyperprior distribution for its training. Let's take a closer look at the updated likelihood model. The first two terms can be lower bounded by the following variational lower bound. From the model standpoint, this is akin to a standard conditional variational autoencoder for frame prediction. However, note that the final term of this updated likelihood is also lower bounded by another variational lower bound, as given by the equation here. This amounts to a nested conditional variational autoencoder operating with sigma Tz as input and producing Bt as output. Combining these two variational lower bounds, we arrive at a combined objective as shown in the equation here. This translates to the evidence lower bound formulation as shown by the equation here. Note that the uncertainty term weighs the L2 loss term in this new formulation. We additionally observed that coupling this generation model with a sequence discriminator, which looks at a set of frames and judges them for their realism, to be a better approach for generating future frames. We augment the discriminator loss LDW with our previous generator loss and arrive at our final objective as shown. We minimize this objective using the Adam optimizer. We evaluate the performance of NUQ and its competing methods for the task of predicting 20 frames given 5 scene frames. We evaluate the different algorithms after training for epochs 1, 5, and up till convergence with varying training set sizes. We evaluate the model performance using SSIM, PSNR, and LPIPs. Experiments are conducted on the stochastic moving MNIST dataset, which is a dataset of 10,000 videos of an MNIST digit bouncing in a box with random trajectories of motion post-collision. Then there is the bear push dataset, which is a dataset of over 43,000 videos of a Sawyer robotic arm pushing objects on a table. And finally, the KTH action dataset, which is a dataset of around 2000 videos of humans performing actions such as walking, boxing, etc. Next, we show some quantitative results of our model vis-a-vis competing baselines. We see that our model outperforms competing approaches on the stochastic moving MNIST dataset even when trained with just 2000 samples, especially in the early epochs. The performance gains transfer when the models are trained on the full SMNIST dataset as well. We observed similar gains for the bare push dataset, and similar observations were observed for the KTH dataset as well. Here are some qualitative generation results of our model and competing approaches on SMNIST trained with 2000 samples. We show diverse generations by our model as well, as highlighted by the green box. Here are similar results for the bare push dataset and the corresponding diversity results. And here are the corresponding results for the KTH dataset. Here we show a video of sample generations by competing methods and NUQ on SMNIST and bare push datasets when each of those are trained with just 2000 training samples. As is obvious, our model generates much more coherent and realistic looking videos as compared to prior approaches. We thank you for your attention, and here is a link to our project page.